So for the final talk today, we have Subhabrata from Harvard, and he's going to tell us about the universality of lentiality.
Thank you so much to the organizers for the invitation. It has been a very stimulating workshop. So I'll talk about universality for these AMP algorithms. This is based on some joint recent work with my colleague, Professor Yue Liu, in the School of Engineering at Harvard, and with Rishabh Dudeja, who's currently a postdoc working with Yue and myself. So Rishabh has been the engine in this ongoing collaboration, and I have been learning a lot from my collaborators, and I hope to share some of my excitement on this with you today. So this is the first time I'm talking about this set of results. So if anything is unclear, just stop me and ask me questions. Okay. Okay, so let me start with a very concrete simulation. So what I do is that for some value of n, I construct a signal vector where every coordinate I sample from this distribution. This is a discrete distribution with some mass at 0, some mass at 12 and negative 12, some at 20, and oh, this should be a negative 20. So this is symmetric about the origin. And then given any particular design matrix, note that I'm not right now saying anything about the distribution of my design matrix. So you give me any design matrix X, I'll generate my data from the linear model. And then I'll consider a regularized least squares estimator. In this case, I use an elastic net penalty with parameters lambda1 and lambda2. And I want to study the behavior of this estimator. Right? And what I want to talk about is the behavior of this estimator under different designs. Okay. So in particular, let me talk about two specific designs, right? The first one is something that we'll refer to as the spike and sign design. So this is a rectangular design where, okay, so what are these objects? So IM is an M by M identity matrix. QM is an M by N discrete cosine transform matrix. Okay, so this is a symmetric orthogonal matrix, completely deterministic. And then S here is a random diagonal matrix square where the entries are plus minus 1 uniform. Okay, so this is one design. The second design, I'll refer to this as the Haar design in some sense. So what this does is that here V is a random orthogonal matrix distributed according, as the Haar distribution. So you should think of it as the uniform distribution on all orthogonal matrices. And lambda is a deterministic diagonal matrix. What it essentially, okay, so in this case, it's a diagonal matrix with m ones and rest zeros. So this is essentially there so that if I look at the matrix X, the covariance matrix of the first design and the covariance matrix of the second design, these two will be the same. But that's all that I do. Okay. Now, what I want to draw your attention to is the fact that these two designs are very different in the sense that they're not even of the same aspect ratio or dimension. They're not even comparable. One is square, the other is a rectangular matrix. Okay. The second thing I want to draw your attention to is the fact that there's sort of very different levels of randomness in the designs. So for example, the spike and sign ensemble has only sort of n bits of randomness coming from these random bits. Whereas the Haar ensemble, in some sense, I like to think of it as having order n square bits of randomness, simply because you can realize a Haar matrix, by constructing a matrix of IID Gaussians and then doing Gram-Schmidt on that. So roughly has order n square bits of randomness. Okay, so these are two of them. You can consider many other ensembles. So my plots don't look good. I hope, okay, so let me explain what I'm doing here. So what I hope to convince you of through these plots is that although these designs are fairly different, if you look at the behavior of the regularized least square estimator or the dynamics of, let's say, the proximal gradient descent algorithm, which solves this minimization problem. They basically exhibit very similar statistical properties. That's what I hope to convince you of. So what am I plotting here? So what I'm plotting here is that, okay, so on the y-axis, I'm plotting the normalized MSE of the estimator that I obtain. On the x-axis, I plot, so what I do is that I keep changing lambda1, which is, one of my coefficients. And I keep the ratio lambda1 to lambda2 fixed, but I change lambda1 and I plot the MSE of the estimator as a function of lambda1. And what I want to show you here is that I've kind of superimposed the performance of many different ensembles, and they basically agree completely. And similarly, here what I'm doing is that I'm plotting the proximal gradient descent algorithm. On the y-axis, I have its MSE. On the x-axis, I'm plotting the iteration number. Yes. But if you look at the sample covariance matrices, then their spectrum are the same. And the eigenvectors are in roughly generic position. So this is sort of something that I would like to explain. Let me show you just a couple of other plots. So what I have here is that, again, for some of these different classes of designs, I can look at the empirical distribution of the estimator that I obtain. And here I'm plotting the histogram of the non-zero entries. And again, you see that as long as the spectra are sort of the same, they kind of look exactly the same. Now, of course, we are definitely not the first people to report simulations of this form. As far as I know, some of the very early simulations on this emerged in the study of noiseless compressed sensing in the work of Zhong and Fan, Monogemy, and others. And Zhong and Fan also have results, rigorous results about noiseless compressed sensing. But here we are, we are allowing additive noise, and we still see that for a variety of estimators. There's nothing special about the elastic net case. If you do it for many other convex estimators, you will see similar behavior. Okay. So why do I think it's interesting and worthwhile to kind of explain this rigorously? So, okay, first is that intrinsically this seems like an interesting observation. But more than that, I feel that to explain this, it necessarily motivates the development of theory to explain this sort of universality phenomenon, that the properties of your statistical methods or your machine learning algorithms don't really depend too heavily on the design. Now, something that came up in Pritam's talk, I think a few days ago, is that if you can rigorously prove such universality phenomena, if you want to understand your machine learning system, you can basically replace it by a more tractable analog. You can analyze it rigorously and then basically take that insight back into the specific system that you care about. Okay. So that's why I feel sort of developing tools to understand such universality properties is useful more generically, even beyond this specific example. Okay. Any questions about this particular simulation setup? Okay. So this is sort of the main takeaway, that if you have these estimators, they often exhibit very, very universal properties, as long as sort of you have matching spectral properties and the eigenvectors are in reasonably generic positions. But now, okay, at this point you might say, well, I might find this interesting, but what does this have to do with approximate message passing? Right. So I'll come to that in a moment. So please hold on to that thought. That will be sort of one of our main motivations. And this will be sort of what guides us in the rest of the talk. I'll probably finish the talk with some rigorous explanations for the figures that I started with, but I'll come back to that at the very end. Okay, so what is AMP? So we saw some of this already in Ahmed's tutorials, and Proga also mentioned these algorithms yesterday. So I'll still sort of go over it very quickly just to set up some notation. So these are basically iterative algorithms. So for example, if you have an instance where you're trying to do an AMP algorithm on a symmetric square matrix M, you basically do the following procedure. At each step, you take your previous iterations, you apply some nonlinearity coordinate-wise. So each of these Z0 to ZT, sorry, this should be T plus 1. So each of these Z0 to ZT, these are n-length vectors. So you stack them together, you get a matrix, and then you apply this nonlinearity, row-wise to each row. You get some n-length vector, then you multiply it with this matrix, and then you do some correction. So Ahmed already explained to us what this correction is and what its role is, right? And this correction is essentially what separates or gives AMP a very characteristic nature in the class of all such matrix vector product style algorithms. So I already explained that FT here is a nonlinearity that's applied coordinate-wise. And GT is somewhat of a very special correction term. It's usually referred to as the memory term or the Onsager correction in the statistical physics world. So what is special about GT? So let me come to this in a moment. So what is special about GT is that if you choose your GT in a very special way, you have an empirical convergence of your AMP outputs. So specifically, if you look at these vectors, if you look at the empirical distribution, then they converge to Gaussians, multivariate Gaussians, with mean zero and very specific covariances. And what is even more special is that typically these covariances can be explicitly described using a recursive procedure that is known as the state evolution. And Ahmed already covered this in the very special case of the symmetric Wigner or Gaussian matrix in his tutorial. Okay, so usually these AMP algorithms are analyzed, and these theoretical guarantees are derived under very special distributional assumptions on the matrix M. Okay, so in particular, the most classical set of assumptions essentially on this matrix M, whether it be a square matrix or a rectangular matrix, was that its entries are IID Gaussians, mean zero variance. And these were originally proposed, I think, in the physics side in the work of Kabashima, and then used in the context of compressed sensing, again in the work of Donoghue, Malecki, and Montanari. The rigorous proofs emerged in the work of Bayati, Montanari, and Bolthausen, and then there has been a long line of follow-up work establishing rigorous guarantees for these algorithms. There has been, extensions beyond the IID Gaussian setting. So one way you can generalize the Gaussian setting is to say, if you give me a symmetric Gaussian matrix, if I look at its spectral decomposition, then I can write it as some ODO transpose. And it's not too hard to see that in this case, the matrix O has like a hard distribution. So it's kind of uniformly distributed on the set of orthogonal matrices, and D has some empirical convergence. In the Gaussian case, it converges to the semicircle law. So you can kind of generalize from the Gaussian case, and you can say, okay, I'll take M to be of the form ODO transpose. O will still be hard, but D in this case will be a deterministic diagonal matrix. I'll assume that its empirical distribution converges to a limit. This need not be the semicircle law. This is a slightly more general setting than the symmetric Gaussian matrix ensemble. And even in this case, AMP style algorithms have been analyzed. So quite a few of these references that I have here were emerged from the physics side and were non-rigorous, and then there has been rigorous results in the results of Ma and Ping, Rung and Schneider-Fletcher, and more recently the work of Zhong. So these algorithms have been proposed, they have been analyzed, there are rigorous results for these algorithms. Okay. So why are they useful in the context of statistical learning, right? So the general premise, and I'll spend just one slide sort of taking a rather high-level perspective here. So why are these algorithms useful? If I give you any learning problem, you can either want to analyze a specific estimator, which might not have a closed form, but might be in the form of an ERM or some such implicit description, or you might want to do Bayesian inference and want to look at the posterior distribution and the expectations of the one-dimensional marginals, right? So to do this, if I just gave you this problem, you'll roll up your sleeves and you'll say, okay, let me bring out all the tools that I know from statistical learning, high-dimensional statistics, probability. I have many different tools to approach this question. So what is rather surprising is that this idea of AMP has proved to be very, very useful for a wide variety of these questions. The general style of this argument is that given a certain target estimator or the posterior mean, let's say, you construct an appropriate AMP style algorithm, which in some sense converges to this estimator of interest. Because of the properties that I mentioned before, you can exactly track the statistical properties of this AMP algorithm. And because it now converges to the estimator of interest, you can kind of transfer these guarantees to the corresponding statistical procedure, right? That's sort of how the argument goes. So this is the general style in which AMP algorithms have been used in various statistical problems and machine learning questions. And this sort of also goes back to the approach that Proga adopted in her talk yesterday, how this was used in the context of causal inference. So I think given this entire discussion, one very natural conclusion that you might reach is that, okay, this class of AMP algorithms seems to give me very, very precise properties of the estimators that I want to study, but at the cost of making very, very strong distributional assumptions on the problem. So I might need to make a very strong assumption that my design entries are IID standard Gaussians, or some very specific form, and only then I get a very precise characterization. And so you might say, okay, this is good, I get a lot of theoretical insights, but maybe I don't really believe my design is Gaussian, right? Maybe I don't believe my features have certain orthogonally invariant properties. What happens then? So what I'd like to do today is to kind of complement that, in some sense, push back on that conclusion slightly. And I'd like to provide a complementary perspective or a complementary application of this idea. Okay. So what I'd like to argue today is that AMP algorithms as such are remarkably universal to the distribution of your ensemble. They don't really care as much. They're very robust. And therefore, because these algorithms can be used to track a variety of statistical estimators, the properties of the estimators will also be universal. Okay. And essentially, AMP algorithms and their universality can be sort of a way to get at the universality of the estimators that you care about. That's sort of the perspective that I'm going to adopt. I'll spend most of the talk today talking about universality of AMP and get at the second part only at the very end, very briefly. But if you're interested, I'm happy to talk about this offline as well. Any questions so far? Okay, great. So, okay. The fact that AMP algorithms, for example, don't really require Gaussianity for the matrix ensembles, for example, this has been known for a while now. So the first result in this direction was by Mohsen Bayati, Mark Lelarge, and Andrea Montanari in 2015, and later by Wei-Kuo Chen and Wai-Kit Lam last year. So they basically prove a result of this form. And this is sort of the notion in which I'll always talk about universality. So let me parse through the result, right? So they say, suppose you consider any AMP algorithm of the form that I mentioned a few slides ago, and assume that your nonlinearities are smooth. And smooth here means, let's say, Lipschitz or pseudo-Lipschitz in the sense that Ahmed described. Assume that you have this symmetric square matrix. Its entries, let's say, are independent or IID, mean 0, variance 1, and sub-Gaussian. So they have sufficiently light tails. So if that's the case, then the AMP outcomes are universal, in the sense that if you take two different matrix ensembles, Mij and M tilde ij, and if you run the same set of algorithms, and if you get two sets of outputs, if you apply some reasonably nice test function f, and if you look at the empirical averages, they converge to the same value. So what this means essentially is that, for example, if you use these algorithms as estimators, if you look at the reconstruction error, whatever is the reconstruction error under one ensemble will be the same as that under the other ensemble. This result by itself tells you nothing about what the actual answer is. It only tells you that the answer is the same in whatever ensemble you choose. But then the advantage is that you know how to calculate the answer in the Gaussian ensemble. So that's sort of this integrable example in your family. So once you know the example in the Gaussian case, you know the answer in every other Wigner ensemble that you have. Yeah.
So just to clarify, so Mij is like the design matrix chosen ahead of time, right?
Yeah.
So this is basically saying that, is it basically saying that like you might as well just choose it to be a Gaussian matrix because it's
in terms of the properties, like if you just care about analyzing, let's say, the reconstruction error of a regularized least squares estimator under these assumptions, if you know that the entries can only be IID, mean 0, variance 1, and some Gaussian, let's say, then you might as well choose it to be Gaussian.
Would choosing the matrix in a different way maybe have some other effect, like that's not related to the convergence of the empirical means? Like, I guess my question is like, does this necessarily say that there's not really like a smart way to choose the design matrix?
So what it says is that in terms of the answer, you get the same answers. But it could be, for example, okay, so I don't know of a concrete example that I can give you right now, but it could be, for example, that for one of these, if you wanted to really calculate what this answer is, there could be some other ensemble for which calculating this answer was much easier than the Gaussian case. So if there were some such thing, and if you could cleverly choose a different ensemble, maybe you could calculate the answer more easily. Other questions? Okay. So this was known, but one restriction of this class of universality results is that it basically tells you that Gaussianity, let's say, isn't really important, but it doesn't really reduce the amount of randomness in the problem. It still basically says, okay, you go from one ensemble with order n square bits of randomness to another ensemble with order n square bits of randomness. The answer stays the same. The question is, okay, what happens if you move to more structured cases? Can you actually have ensembles with much less randomness that basically exhibit the same properties? Right? And if you remember in our initial simulations, we had this spike and sign ensemble that basically had only order n bits of randomness, but still seemed to exhibit the same kind of properties, right? So that's what we are interested in. So what I'll do for the main part of the talk today is to introduce this family of what we call semi-random matrices. And I'll analyze a very simple class of AMP algorithms. And I'll exhibit that these AMP algorithms are universal for all these semi-random ensembles. So My choice of the AMP algorithm will be a simple choice, but that's just for convenience. In follow-up work, we've been able to generalize it to a broader class of algorithms. But for the purposes of the talk, I'll restrict myself to a simple case. The main ideas that I hope to communicate are the notions of semi-random matrices, what they buy us, and why we are able to prove this universality. That's sort of the main goal for me today. And throughout the talk, basically, universality will be in the sense that I described in the last slide. So two classes of things, if they have the same properties, if you run AMP algorithm on any two such ensembles, you will get the same output. That's the style of results I'm going for. Okay, so the class of algorithms that I'll look at are these so-called memory-free AMP algorithms. These particular ones were introduced by Chapman and Hopper, and their validity was later established in the follow-up work by Zhong and Fan a couple of years ago. So what these are algorithms with a very specific flavor. What are they doing? So they basically say, you again update your algorithms. These are basically like, okay, you have ZT, you apply some nonlinearity coordinate-wise to this vector, you multiply it with some matrix M, and effectively that we would like to call that to be ZT plus 1. But there is some small thing that you have to correct here. I'll come back to this in a bit. Yeah, this is not really that important. You should really think of it as an algorithm that I get by taking a vector, applying a nonlinearity, multiplying by a matrix. Style of the algorithm. Okay. So why this specific choice? So if you go back and think about it, when I initially introduced the AMP algorithm, there was a certain correction term, right? The Onsager correction that I described. What is special about this particular class of algorithms is that I don't need to worry about the Onsager term. That's what's special. Now we also know how to handle cases where there is a correction term. So we can talk about that as well, but I'll restrict myself to this class of algorithms for simplicity.
Kind of projection of the F out of the class space meant by CT.
Right, in some sense, because so roughly this leads to what is called the divergence-free criteria. I'll come to that in a few slides. So essentially, the idea is you want to assume that F is, yeah, so exactly the projection of F on the Gaussian space to Gaussians with a very specific variance that has to be 0 on the first Hermit polynomial. That's basically what this is doing. Okay. So this is the algorithm. This is the most important notion I hope you'll take away from the slide today. Okay, so there's a few different notions out here. So let me go over it very slowly. And if anything is unclear, please do stop. Okay. So the ensemble that I'll consider, this is our class of semi-random matrices. So we want M to be of the form S psi S, right? S will be the random part in our description. This is the random part of the semi-random ensemble. So it's a diagonal matrix. Every entry is IID plus or minus 1. Okay. The matrix psi here will be completely deterministic. So the ensemble has only order n bits of randomness. And then I'll make some structural assumptions on the matrix psi. So specifically, what I'll assume is that the matrix itself is delocalized, roughly at the order 1 over root n. The operator norm is of order 1. And essentially what conditions 3 and 4 tell you is that if you look at the matrix psi transpose, then it basically has to look like a diagonal matrix with all equal entries on the diagonal in the L infinity norm. That's roughly what 3 and 4 are telling us. Okay, so roughly what 3 and 4 are telling us is that if you look at psi transpose minus some constant sigma psi squared times identity, if you look at the L infinity norm of this, then this has to be small. Okay, so I write it differently. So let me just say this is small, because I have slightly different requirements on what happens on the diagonal and the off-diagonal entries. But this is roughly what this is saying.
Infinity is just the
Entry-wise, yeah. So that's why here I have off-diagonal entries. You take the maximum of them, the diagonal entries. So I don't really need any rate of convergence on the diagonal entries, but the off-diagonals I need something basically like 1/√10.
So why do you say it's small versus sigma squared can be infinity, can be very large?
So sigma psi squared is some
Yeah,
fixed constant. Okay, something like 10. 5. Any questions regarding this definition? This is sort of the only thing that I hope you will take away from this talk. Okay. So our main result, one of our main results that I hope to talk about today is that if your matrix ensemble M is semi-random, and if your non-linearities are smooth enough, and if you start from some IID initialization, then your outputs will be universal. So what this is roughly saying is that if you start from some IID initialization for any two semi-random ensembles, you will basically get the same answer, provided these two ensembles have the same value of sigma psi squared.
This is great. Like, does this mean if I look at a optimization problem that like a quadratic form in M,
Yeah.
Plus minus 1 on the hypercube, and I look to maximize it? This is an SK model, but for that matrix. Does that tell me? Does the result tell me that the value is the Fruity formula?
Yeah, so for example, for that, yeah. So for example, one of our applications, we do it a bit in our paper, but so one of the main applications, for example, that Opper and Chakmak had when they looked at this was, so there was some prior work in physics by Parisi and Potters and Parisi, Marinari and Rittort, I think, where they looked at, SK type models with very deterministic couplings, and using simulations, they had basically predicted that these models should also exhibit the same properties as SK, or SK-like in some sense.
So you get the same value, like the study you're going to get the exact.
Right. So the only caveat here is that physicists didn't have the sign. We still need to sign things. So on the signed version, we do get and I can come back later to whether you need signing or not. That's something we've been thinking about quite a lot recently. But at that level, things are okay. Yeah.
So how should I think of the condition on psi? Is it like, should I think of this as roughly sort of a diagonal sort of D1s being roughly similar?
Yeah, so I'll come to examples right now. So hopefully that will clarify this a little bit. Other questions? So here are a few examples. I'll do a few examples. So one example here is that if you have a matrix psi, which is a symmetric orthogonal matrix, and if this is delocalized, then if you sign it, then you get a semi-random ensemble. So for example, if you have like a discrete cosine transform, a discrete sine transform, a Hadamard-Walsh matrix. These are deterministic matrices. You take them, you sign them, you will get the same thing. That's one direct application. A second one is, and this is sort of what we are really going for. So one of the ensembles that I described before were matrices of the form OD, O transpose, where D is a deterministic diagonal matrix and O is hard, right? And I told you that this one example people really understand well. So what I'm saying here is that you don't really need O to be hard. Okay, this is not really important. As long as the eigenbasis is sort of a delocalized matrix. For example, if it's just sign and permutation invariant, you'll still have the same kind of properties. So har isn't really important. Much less randomness still will give you the same results. Okay. And then one of the applications, so when Chakmak and Hopper applied their AMP algorithms, so there is a slight difference from the algorithm that Ahmed presented in his tutorial. They don't, so Bolthausen's algorithm works directly on the matrix J in some sense, but Chakmak and Hopper's algorithm works on the resolvent rather than just on the matrix. But doesn't really matter. If you take this symmetric matrix, as long as square root n Jij has finite moments of all orders, if you look at these resolvents, these are centered resolvents, you will still have the semi-random property. So there is one slight issue here. Because of the signing, I need to assume that Jij is symmetric about 0. I don't think this should be required. I think this is an artifact of our proof. But morally, this is sort of what it tries to get at.
So to prove that a matrix ensemble is semi-random, you just multiply it by diagonals on both sides and then show that that has small spectral norm and those things that you wrote down.
Yeah. That's all. That's sort of why we can verify it. So for example, I think the heaviest machinery we need is actually for the IID ensemble, because to show the kind of delocalization thing, we really need to rely on like recent advances in random matrices, like local versions of random matrix results and stuff like that. But the others are actually the concentration inequalities. So it's fairly easy, I would say, to verify it.
Assume that initialization is Gaussian, but you have Lipschitz function. Right? So
right.
That means like Lipschitz function Gaussian. You can characterize that.
Yeah, so right. We realized this after we put our paper out, which kind of, in hindsight, seemed a bit stupid. But the thing is, one of our restrictions is that we can apply only the same function to every coordinate, right? So I could rephrase my result to say that I start from a constant initialization. That's kind of one of the things, but you're right. If I apply a Lipschitz function, then I can generalize the class of laws, IID laws from which I start. So there is nothing very specific about Gaussian. I can introduce an initial iteration and change things. But I stated it in the form of Gaussian because, as you see, that's kind of used in our proof. So I wanted to state it in that form. Okay. Any questions? Okay, so let me spend maybe the next 10 minutes giving you some ideas for the proof. So the proof essentially has, 3 steps, of which I think basically the third step is the real challenge. The first one is to basically say that, essentially say that if I can do it for some functions that have some special properties along the lines of what Song alluded to a while back. So if these are like divergence free, I'm basically done. And the second step is basically like a normalization step and an approximation step. Basically saying, okay, I am applying these nonlinearities. If I can do the proof for polynomials, I'm basically done. And okay, some other normalizations that we'll see in a bit. The critical step in this entire proof was the proof with, once you have done all these normalizations, how do you go about it? And we'll see that the main workhorse for us is like a method of moment style argument along the lines of what Ahmed already mentioned earlier this morning. But there are some subtleties there. I hope to, I'll do a very simple case, but I also hope to tell you briefly about what the challenges were for us. Okay, so what is this term essentially doing? So suppose you're willing to assume, and I'll do it inductively, so this is okay. Suppose I have done everything up to time t, right? If I have done everything up to time t, then I basically know that Zt is empirically like a Gaussian with mean 0 and variance sigma t. I already know that. So if I know that, then I know that this term basically behaves like sigma t squared. And if I look at this inner product, then it basically behaves like sigma t times expectation, where z is a standard Gaussian. So effectively what it says is that this term is like m times some function f tilde, where f tilde satisfies this divergence free condition. So the reason I didn't start with this description is that it requires me to tell you a priori what this sigma t is, but it's basically what you get out of state evolution. So the first simplification that I'll do is to say, okay, henceforth I'll assume that my algorithm is of the form zt plus 1 is m f tilde zt, where f tilde satisfies this divergence free condition. The second step, okay, let me not even talk much about it. I'll basically assume that these nonlinearities can be replaced by polynomials. That I think everyone here can believe. Another thing I'll also assume is that, okay, I said that the diagonal entries of psi transpose need to be close to sigma psi squared. So I'll assume that, okay, they're exactly all equal to sigma psi squared. That also introduces some vanishing error that you can track. And then you can do some normalization. So you can set that sigma psi squared is 1 and sigma 0 squared is 1. That like introduces some scaling that you can adjust later. And finally, I'll also do, I'll also assume that these nonlinearities, which are now polynomials, they basically are unit norm with respect to standard Gaussians. And that's essentially also just a normalization. But what that buys us is that it now gives us a very specific target. Once you allow me to make these three assumptions, I can conclude from the state evolution equations that now I'm basically trying to prove that Zt is a mean 0 variance 1 Gaussian. Once you allow me these normalizations, I know what my target is, and that becomes crucial. Okay, so now, okay, I'll do it for the unit marginal case. I'll do the most obvious thing. I'll prove that if you want to analyze what happens to this empirical average, you just need to analyze what happens to the expectation. And this will follow just by some out-of-the-box concentration inequality, Efron's time, something like that. And the expectation here is just with respect to the random signs and the randomness in the initialization. Those are the only two things that we have. Great. So why did I make a big deal of the normalization step 2 slides ago? Because now I know that these ZITs are basically going to behave like standard Gaussians. So to do this step where I have to analyze this empirical average, I will only do it for polynomials, and in particular, I'll do it for Hermite polynomials. Right? The advantage of doing it for Hermite polynomials is that we'll do this analysis in a method of moment style, so I'll know precisely what targets I'm looking at. If I did it normally, I needed to match it to moments of the Gaussian. That's somewhat more complicated. I'll instead show everything goes to 0. Just helps with the proof. Okay, so let me do a very simple example. So suppose my test function is just x and f. So I'll go up to the second iteration. And let's say f1 and f2 are these two functions. Okay, you can check that they satisfy whatever assumptions I needed. These are polynomials. Things are nice. So, okay, what do? I start with my average. I unroll the operations. I expand it. And I eventually get some expansion in terms of the matrix entries and the initialization. Okay, great. This is also what Ahmed mentioned earlier today. Now, what you do is that you take the expectation, right? You take the expectation with respect to the signs, and you take the expectation with respect to the initialization. So the Mij's contain the signs, and the Z0s are IID Gaussians. Once the dust settles, you just have some expression in terms of the entries of your delocalized matrix psi. That's what you need. And now, for example, I would need to prove that this thing actually converges to 0, right? That's what I would need to prove. So in this particular case, I can get lucky in that I can basically bound this by a crude triangle inequality bound. I just bound every term by an absolute value, and then I have the delocalization estimate term by term, and then things vanish. But this is sort of really special. This doesn't happen always. The problem is that when you do this unrolling operation in general, and once you express everything in terms of the initialization Z0, you're gaining polynomial numbers of terms at each step, right? So if you're not careful, and if you just put a crude absolute value bound at this step, sometimes, and in most cases actually, the polynomial growth in the number of terms that you have will kill you. And these decays that you get from individual terms, they don't really give you enough gain, right? So what we have to do is to actually crucially track what happens with the cancellations. And we crucially here use the fact that psi transpose essentially looks like some constant times identity. This is where that comes into the picture. So you have some cancellations coming from the terms where things converge to a diagonal entry. You have some things, some cancellations coming from the fact that of diagonal entries of psi transpose are close to 0. So we have to kind of track that, and we have some combinatorial scheme to actually get at that. So this, what I have here on this slide is slightly misleading. It gives you the sense of, what we want to do, but this strategy does not work in general.
So what works?
Yeah, so we have to kind of keep track of these. So what ends up happening is that once we extend things, we still track it in terms of these decorated trees. And then these cancellation operations that I mentioned, they come up as combinatorial operations on the tree. So for example, the fact that psi transpose diagonal entries are 1, when you sum up those things in terms of the tree, we can visualize it as, you have 2 of these leaf, sister leaf nodes, you kind of collapse them. So you prune the tree. So you kind of prune the tree, and in some cases you do some cancellations. We have some scheme to keep track of it combinatorially, but once you do that, the cancellation does happen. This I think was the step that was actually a bit magical for us when we did this. Okay. Any questions? Comments? Okay, so now sort of parallel to what we did, sort of very close to when our initial work in this direction came out, there was also an independent approach for universality of these algorithms that was introduced by Tianhao Wang, Zhong, and Fan. So they actually have a slightly different approach. There are some, okay, so what do? They analyze both universality for AMP algorithms with IID matrix entries and for these orthogonally invariant classes. So they do both. For the IID setting, they actually improve the existing results quite a lot, and they prove that even if the entries are, even if the matrix is the adjacency matrix of some sparse random graph with diverging degrees and things like that, so very general Wigner matrices, you still have the same result. So I think this definitely fills in a very important gap in the existing literature. I I think there are some slight differences between the two approaches when it comes to these orthogonally invariant designs. So we are still trying to understand what the similarities and the differences are. At a high level, there is some similarity because they also do an unrolling kind of operation. So they expand things out and then do a combinatorial step. So at that level, these two approaches seem to be a bit similar. But so far as we understand, there are some crucial differences. In particular, I think their approach crucially utilizes the randomness in the matrix rather than in the initialization. And as a result, they in some cases need more randomness than what we can handle. Okay, so for example, the semi-random ensemble that I described to you is actually much less random than sort of a competing class that they handle. But as an upshot, their combinatorial analysis can be a bit more streamlined. So I think these are two parallel lines of work, and I think it would be very interesting to see how they compare with each other moving forward in terms of when they can be used. So this is parallel work. I'll take 2 minutes and tell you about. Okay, I'll revisit the initial simulation to basically say, why are these connected? So let's go back to our regularized least squares problem. And basically, what we can prove, and this is actually a very new result. Hopefully it will come out on arXiv today or tomorrow, hopefully soon. So what we can prove using the same style of analysis is that, okay, so you have your design matrix in regression. You express it as some j times s. So s is this sign that I need. J is a deterministic matrix. And what I'll assume is that if you look at the matrix J transpose J raised to the power k, then it's close to some constant times identity for every k. Okay, and this constant essentially is the kth moment of some measure. So you should think of this measure as the limiting spectral distribution of the sample covariance matrix, right? And putting this condition for every k is sort of like putting it on the matrix resolvent, but we just found this form to be slightly easier to work with. I think it should be possible to go between one form and the other. At a very high level, our result basically says that if the loss that we are looking at is strongly convex, then we can use these AMP universality results to basically conclude that restricted least squares estimators will also be universal. And you can get this strong convexity either if the regularizer that you have is strongly convex, or if you have, if your problem least squares part is well conditioned, you'll get this.
So under prime factor,
right, I don't have it right now. And I can expand more on that. I don't have it yet. Because it requires us to prove something about the state evolution equations and their uniqueness. But if it's elastic net and stuff, you're okay. In the initial simulations that I showed you, actually, we ran elastic net, but with the ridge part very, very small, like 10 to the -3 or something. And you basically still see the same thing. So I think it's going to be the same, but formally, I don't have the proof yet. So to conclude, basically, the main takeaways are that, AMP algorithms are quite robust. They don't really depend too much on the laws of these ensembles that you work with. The strong distributional assumptions that we see in practice, or see at first, are basically there to let us characterize their properties. And the fact that these algorithms can be used to track statistical estimators can allow us, in fact, to take these guarantees for AMP style algorithms and transfer them to the statistical estimators that we care about. We did this in the context of the linear model. I think it would definitely be interesting to go beyond this structure and to actually handle what happens for base posteriors. And okay, there is this question that has been gnawing at us, which is, do we need the signing? What happens if you have completely deterministic ensembles? We have some preliminary thoughts on this. I'm happy to expand more on it, but that's sort of where we are. Thank you so much for your attention.
Well, about this signing question, so if you just look at the problem where you're interested in binary vectors, so SK or something, then the signing doesn't matter. You can just do change the variable.
We thought of this. There was some annoying issue which still bothered us. I think it was because, okay, so we were looking at the AMP algorithm that tries to get to the solution to the tap equations, right? And that no longer works just on the hypercube. That like works on the solid cube. So there was some difficulty related to that. That's why we kind of ended up still leaving that assumption. But I kind of view it more as a technical barrier in what we did. Yeah, I think one question that we find actually really intriguing is, okay, what happens if you don't have these signings at all, and whether it is possible to replace these signs by additional assumptions on the deterministic part. Not really clear to us at this point.
Also, you said you can generalize this to the iteration where you have literature, and where nonlinearity is going to have multiple.
Yeah. So when we did, so for the regularized least squares problem, for example, the algorithms that we need to consider, what we do is that we can handle history now. So if you have history, you can kind of encode, the correction terms in them. So that sort of really helps us simplify things. It kind of, so what happens is that if you have history, then when you do the combinatorial analysis, that becomes a bit more complicated down the line. But at least in this linear model setting, that still is tractable. So I think going beyond that, one needs to see.
Good. There are no questions. I'm the speaker.